Welcome back. This is the second video for Unit 2 Free Fall. So we are on page 2, and in this area we are going to do some data for a classroom experiment. So do not draw this, but basically we have what's called an air track, and we're going to set it at an angle. So here's the surface, and so we have this, and we're going to put an object on here that will slide down at a certain velocity, or it will accelerate at a certain rate, rather. So this is something we'll do in class, and so we will be skipping the data right here for now. So we were looking at a formula. Remember the formula we came up with previously. Acceleration equals twice the distance times the square of the time. And you've got this on the previous page. So here's how we're looking at it. The data, we'll look at it, but the distance that we used was going to be the same the whole time. And the time should have been the same amount of time for each run, which means that 2d over t squared is constant. And then our acceleration is constant. This will make more sense after we do the actual experiment in class. There's something tragically wrong with our experiment. Our original goal here with the air track was to prove that free fall is uniform acceleration. How does a glider sliding down an air track prove anything? Galileo obviously didn't have an air track, so he used a ball rolling down a ramp. He did the experiment with the ramp at a 10-degree angle, and it worked. He did it at a 20-degree angle, and it worked. It worked for 30 degrees and for a 40-degree angle. But eventually the ball started slipping on the track at steeper angles. It didn't stop Galileo from claiming success. He extrapolated the results of the 10, 20, 30, and 40-degree angles to say that his experiment would work even if the angle was 90 degrees, which is free fall. Real quick, an idea of extrapolation. Don't draw this, but if you had a graph, and let's say we had a few data points, let's make them better than that. So here's a data point, here's a data point, here's a data point. And we can draw a line for that. And extrapolation is when you look at something beyond it. So what would the value be here? We would look up and we would say that here's where the point would be, and then we could draw it back over. That's what it looks like when you extrapolate. Galileo's claims were finally accepted. Free fall is uniform acceleration. He wasn't able to determine a numerical value for the, quote, acceleration of gravity, but we now have a very accurate value. Earth's acceleration of gravity, 9.80 meters per second squared down. Or you could say negative 9.80 meters per second squared. The negative would be implying the down direction. In terms of feet, 32.2 feet per second squared down, which you could call negative 32.2 feet per second squared. Now, we really don't use feet in this class very often, but you have the number here. Acceleration of gravity in feet, we usually round it just to 32 feet per second squared, negative 32 feet per second squared. An approximation that we will use most of the time, the acceleration of gravity is negative 10 meters per second squared. Negative 9.80 rounds to negative 10. 10 is a very nice number to make approximations. It makes things a lot simpler. And so a lot of times we will use negative 10 meters per second squared. A lot of physics books use this notation for the acceleration of gravity, lowercase g. So this means that a t-table for free fall might look like these. Time versus velocity, so 0 seconds, 0 meters per second. What this tells me, if when the timer starts it's not moving, that it is a dropped object. When you drop something, its initial velocity is 0. So with an acceleration of negative 10 meters per second squared, after 1 second, our velocity is negative 10. After 2 seconds, our velocity is negative 20. And this is telling me that with every second, our downward velocity is increasing by 10 meters per second. So negative 10, negative 20, negative 30, 4 seconds, negative 40, 5 seconds, negative 50. Looking at this other t-table, at time 0, we have a velocity of 23 meters per second. This is positive. So with our acceleration and with our velocities, negative means down. So positive means up. So at the initial time, this has an upward velocity to start with. And what this tells us is that it was thrown upward at 23 meters per second. So this is what's going on. So after 1 second, our velocity has decreased by 10 meters per second. And so we end up with a velocity of 13 meters per second. Another second later, it's gone down by another 10 meters per second. At a time of 3 seconds, it's gone down by another 10 meters per second, and now it has a velocity of negative 7. At 4 seconds, negative 17. At 5 seconds, negative 27. Here's what this is telling us, is that we have a ball, and it goes up, and then it stops, and then it comes down. And it looks like it's maybe about right here when we stop making measurements. So here it's going 23 meters per second. It's slowed down to 13. It's slowed down to 3. It's gone past the peak. Now it's at negative 7, negative 17, negative 27, speeding up in the downward direction as it falls again. We are going to work a lot of examples involving distance, time, velocity, and acceleration. Some of you will want to rely on the formulas to work the problems. Others will want to do as much calculation as possible using some fundamentals and definitions. But we'll need to rely on a formula once in a while. So we need to develop some formulas before we start the examples. Okay, so back to our earlier derivation. Average velocity is distance over time. Acceleration is final velocity minus initial velocity over time. And for uniform acceleration, the average velocity, we add the final and the initial velocities and divide by 2. Now this is for motion that is not starting at rest. So VI is not equal to 0. If you want to see how we derive these formulas based on these 3 formulas, maybe you could come see me at another point in time. But using these 3 formulas and rearranging them, we can derive other formulas. So final velocity equals initial velocity plus the acceleration times the time. Here's one important formula, and it comes from rearranging the acceleration formula. Another formula, distance equals initial velocity times the time plus 1/2 acceleration times the time squared. Another important formula. And all of these things together give us final velocity squared equals initial velocity squared plus twice the acceleration times the distance. So these are 3 of our most important formulas for Unit 2 and as we continue on through this course. You don't necessarily need to memorize these formulas. They're on formula sheets, on quizzes and tests. They're in your notes when you're doing homework. But it's important that you know how these formulas work. Especially, one of the first things you need to know how to do is how to select the right formula for the problem you're doing. So general formulas for accelerated motion. These are the general formulas. So final velocity equals initial velocity plus the acceleration times the time. What this formula does, I'll write it in a different color. This formula relates final velocity and time. Our next formula, distance equals initial velocity times the time plus 1/2 times the acceleration times the square of the time. This formula relates distance and time. And finally, final velocity squared equals initial velocity squared plus twice the acceleration times the distance. This formula relates velocity and distance. These are the general formulas that we use through physics. We have specific versions of these formulas for motion that starts at rest. At rest meaning that initial velocity equals 0. So using the formula that relates final velocity and time, final velocity equals and initial velocity is 0 because we're at rest. So final velocity equals acceleration times the time. In our distance and time formula, distance equals initial velocity is 0, so this entire term disappears. Distance equals 1/2 times the acceleration times the square of the time. And our velocity and distance formula. Final velocity squared equals initial velocity squared is 0 equals twice the acceleration times the distance. So these are for specific use when we are starting at rest and initial velocity is 0. These are our general physics formulas that we can use in any circumstance. The acceleration of gravity on Earth, again, the number we typically use for this class, -10 meters per second squared.